This episode is sponsored by Indeed Prime. Indeed Prime helps software developers simplify their job search and land their dream job. Candidates get immediate exposure to the best tech companies with just one simple application to Indeed Prime. Companies on Prime's exclusive platform message candidates with salary and equity up front. The average software developer gets 5 employer contacts and an average salary offer of $125,000. Indeed Prime is 100% free for candidates, no strings attached. And when you're hired, Indeed Prime gives you a $2,000 bonus to say thanks for using Prime. But if you use the SE Radio link, you'll get a $5,000 bonus instead. So sign up at Indeed.com/SERadio. This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
Welcome, listeners, to another episode of Software Engineering Radio. Today I'm talking to Camille Fournier, who until recently was CTO at Rent the Runway, where she led a team of over 60 engineers who were responsible for both the customer-facing technology as well as the custom logistics system. Prior to that, Camille served as a software engineer in Microsoft and most recently as a vice president at Goldman Sachs, where she dealt with risk technology and technology infrastructure. Camille is very well known within the tech community, speaking on a variety of topics such as distributed systems and technology leadership. Camille received a bachelor's degree in computer science from Carnegie Mellon University and an MS in computer science from the University of Wisconsin. She's currently a member of the Apache Software Foundation and lives in New York City with her husband and son. Camille, welcome to the show.
Thank you for having me.
Our topic today is real-world distributed systems. Could you start us off by briefly describing what a distributed system is?
Sure. So my favorite definition of distributed system comes from Leslie Lampert. He was one of the famous, sort of early researchers in the field. And he describes a distributed system as one in which the failure of a computer you didn't know existed can render your own computer or machine unusable. So I love that definition because I think that people can get very hung up on distributed systems being about there's a network in the flow. So, if you are talking over the network to a database, you are in a distributed system, for example. Even when you were in like old school 3-tier architecture land, right, where you were building some kind of a view layer and an application layer and a database layer, and if those went over the network to talk to each other, but even if there were only like 3 of them or even 2 of them, that is technically in some ways has some of the complexities of a distributed system because you are going over the network. There are more failure domains. But the reason that I like the Lampert description, where it's the failure of a computer you didn't know existed, is that it really gets, I think, to the heart of when distributed systems become more than just another little thing that can fail and something where you have so much more complexity than it's possible for you to easily reason about. I think that's really that tipping point, right? When you don't know exactly, you're calling systems that are calling other systems that you don't even know about. And, some downstream system's failure can cause you to be failing. And, you didn't even know that downstream system maybe even existed.
Do you think it would be a fair assessment to say that we all are building distributed systems all the time? Because by that definition, there isn't really anything left that doesn't talk to something else that you don't know the details of.
So I think, yes and no. I mean, look, for this novel writing thing, not a novel, book writing thing that I did in November, I used a piece of software called Scrivener. It's a text editing, made for people writing long works, whether you're writing books or you're writing screenplays, it's made for that, right? If you're writing a Scrivener type program, you're probably not worried too much about network stuff, right? You're worried about writing to disk. As long as the operating system that you're writing this thing for is reliable, then your program is going to install on this person's computer and work. And there's less and less software like that these days because we're all building these cloud-aware, blah, blah, blah systems. But I think there is something to be said for don't worry about problems you don't have yet. And even though you can be building even a networked piece of software that will have some complexity, that doesn't mean that you have to engage with the entire world of distributed systems complexity to build that software, to build it as well as it needs to be built and to make it usable.
So when do people have to worry about this thing? What is the tipping point? What's the threshold that you have to cross when the simple thing where we really don't worry that much about parts of it being distributed turns into something where it really becomes a major issue and you need to be aware of it?
So I think that that's a good question. So I think that the tipping point tends to come when you really have many different systems that you or your team or your software is run across. So anyone who's working in a services architecture, especially a microservices type architecture, you're starting to get some of that complexity. Doesn't mean you're embracing all of it, that you need to be embracing all of it, but you're starting to get some of it. Versus, for example, if you're building like a code that runs in a web server and you happen to run that web server horizontally scaled so that you can have more people accessing it, but you're not sharding your database, you're not using multiple different data stores, the distributed systems problems that you need to be engaging with in that horizontally scaled, but maybe not that complex web server, they're just a different scale of distributed systems complexity. So, it kind of it'll come in a little bit depending on what you're doing, right? If you're working with a database over the network, you need to understand the way that failures are communicated to your client. So, if you do a request to that database and the network drops out, how do you figure out whether the request succeeded or failed? There's a little bit of a distributed systems complexity there, even if you're just doing the simple, 3-tier architecture kind of model. But you probably don't need to worry about really, really detailed, transaction retries and, storing extra state around multiple different versions of the same data because it's spread across multiple different machines that may or may not be in sync, may or may not be able to communicate with each other, right? There's distributed systems are as much an engineering problem as they are a theory problem. And that means that you're going to apply as much theory as you need to solve the engineering problem, but you don't want to apply a lot more.
Mm-hmm. So some people say that you have a distributed system as soon as a web browser enters into the picture because the browser as a client accesses your server, voila, a distributed system. Would you agree with that? Or is that an example of something where you'd say that it is technically but not practically relevant?
Yeah. I mean, I guess what I would ask is so what's the point? What are we getting from making that statement? What are you trying to teach developers about when you make that statement, right? What are you trying to get them to be aware of? What kinds of things do you think they should be worrying about that they're not worrying about normally? Because I think that's a more useful thing than saying it's a distributed system. It's like, yeah, okay, it's a distributed system, so what, right? If it's a distributed system where you are never caching state that you're trying to modify within the browser, then kind of does it matter that it's a distributed system, or do you just need to think about don't try to, cache a bunch of state, do a bunch of modifications on that state in the browser, and then talk to the web server, and then, because you could fail, you could lose all that state that you cached because the customer closed it. I make a point in one of my talks. I think that people really underestimate humans' ability to have intuitive understanding of systems that they're very deeply familiar with. And I think that includes both developers and users of certain types of network software. right? Like, we all understand that if we are typing something in our browser window and the browser window crashes, it's likely that we will lose that data. We understand that just because it's happened to us a bunch of times, probably. Like, we may not understand the reasoning behind it, but we know that that will happen because it's happened to us in the past. So we know that it's a risk. So as users, we know that it's a risk and we'll get really annoyed when it happens. And then as web developers, we also know that it's a risk. And we know that if we're doing something where losing that state halfway through matters, we're probably going to be more actively sending it over to the server versus, well, whatever, I'm just building some little thing. And, if the browser crashes, the user's got bigger problems. I don't care. Like, they'll come back to me or they won't, whatever. Right. So I do think that you can't underestimate people's intuitive understandings of the problems in the spaces that they work in every day. And that sometimes we get really hung up on the jargon of distributed systems, maybe because it sounds cool or it's hard or complex or whatever, without thinking about, but how is this useful to the people who are working every day, just trying to make good systems that their customers are going to want to use, that, are going to mostly do the right thing within reasonable failure domains.
Mm-hmm. Okay, so let's talk about situations where we actually have crossed that threshold, where we are actually building something where the fact that it's a distributed system becomes important. What are some of the challenges that people can run into, and how would you address them?
Sure. So I think that the challenges that people tend to run into, especially when they get to these really large scaling systems, so let's back up and say, why do people build these distributed systems? When you think of the classic distributed system, you're probably thinking of the Google scale systems, right? That they built, and they've written a bunch of different papers about what they do, right? Or maybe you're thinking of Facebook scale systems, or Twitter or whatever. You could think of these, or Netflix is a great example, right? You imagine these just clusters, data centers full of computers running bunches of different code that's all sort of working together to create some kind of experience. And so one point that I like to make is, when you think about why these companies built these systems, why they went to distributed systems, they kind of went for two reasons, right? They went because they needed to scale, because they had problems that would not fit easily on a single machine. They had more data, they had more volume of users, they had more computation, whatever. Or they also needed failure tolerance. So they wanted to have a really highly available 24/7 system where if a machine failed, if something failed, the system would survive a certain amount of failure. So the challenge is, of course, that scaling and failure tolerance make each other harder. Right? So as you scale, you put more machines out there, you put more network out there, you have more moving parts, you have more complexity, and you have more places for failure to happen. Right? And there are just countless postmortems out there from big distributed systems, vendors, from Amazon, from Netflix, from whomever, where they talk about, so this other system that we build, that this third system relies on, it had some network issues, or it had some disk issues, and so it's sort of degrading its performance. And then the other system kept trying to hammer it, and it didn't back off, and it caused this other system to start having problems, and thus we had downtime, basically, right? You see these, really interconnected, complex parts working together, and they can fail, right? Each one has their own independent failure domains. And it's really, really, really hard to write a system where you think about all of the possible failures that can happen to you and that can happen to tertiary systems and account for all of them. Nobody does that perfectly, right? Even the best developers, the best companies, nobody does that perfectly. So you've got this massive scale, which makes failure harder. Okay, so how do we deal with failure? The ways that we deal with failure tend to make scaling harder, right? We put a bunch of redundancy in. We write data multiple places. All of a sudden, you're doing more work. You've added more overhead to make sure that when you do fail, you don't lose data, or you lose less. You have some redundant work going on, so it's less likely that you're going to fail in all of these different ways. But okay, well, now you've made it so that your scaling is less efficient. You have to have more machines to scale the same amount. So, it's these two elements are the fundamental goal of building these big distributed systems, but they're also fundamentally in conflict. And what you see is people really decide on their distributed system, usually balancing those two things. They decide which of them they care about more to some extent. It's almost like a slight rephrasing of the CAP theorem, is one of those famous distributed systems, pieces of research, right? Which says that you basically, if you have a distributed system, you really can't get rid of the P as partition tolerance, and you have to be able to withstand some kind of network partition, or you're not a distributed system. Okay, so ignoring the P, you have C of the consistency, meaning can you lose data? Can you have people read data at the same time and see sort of different results? Where does that fall out? And availability. How many degradations, how many failures can you tolerate and still serve responses to clients? And so most people are sort of twiddling between those two axes, right? To make sure, we can show some stale data or even potentially lose data. That's better to do that than to not have something that responds to our clients. Or, we'd rather, if we lose a majority of nodes, not be available at all, because that would reduce our ability to be, consistent in the way that our clients are expecting. So you're really balancing between those two things as you decide how to really structure and architect the distributed system that you're building.
Mm-hmm. It seems to be implicit in what you just said is also a trade-off or an axis from simplicity to complexity, right? So things become much more complex, and so you add lots of possible things that can fail. That makes a lot of sense.
Mm-hmm.
So, as you said at the beginning, that this is what Google and Facebook and Netflix face. Do normal people face it as well, or is it really just only if you're building a global scale system?
So normal people certainly face it. I think that normal people face it when they build out services architectures, whether or not you call them microservices. I think services architectures are a very sane way to think about software at a certain scale. And that scale does not have to be Netflix scale. That scale does not have to be massive scale. It should probably be more than proof of concept scale, right? It's not clear to me that you should start writing your software in a services architecture. But once you've proven out and gotten to the situation where you have 30, 40, 50 developers, there can be a lot of value in thinking about the entities of your system that can operate independently and pulling those into services, and writing a system that joins those entities as necessary and allows sort of independent development and independent ownership of data instead of a big monolith. You can do monolith. Nothing wrong intrinsically with monoliths, but I think in the way that modern software developers tend to build software and the kinds of problems that we're solving, and the increasing sort of ease of creating a distributed system. I think, one thing that I want to make a point on is, I think the reason that you see so many distributed systems today is not just because people have the need for more scale and they have the need for more, failure tolerance or what have you. It's actually that it's just easier to do it because we have the cloud. And it's easier to get access to hardware, and it's easier to get access to network-attached servers and network-attached disk and the network. And there are more, systems out there that are distributed systems themselves for data storage and data processing. And so everybody's already starting, in a way where it's very easy to build a distributed system, at least from the hardware accessibility perspective, which was not the case 10 years ago. Right? 10 years ago, pre-cloud, it was very hard to get your hands on the kind of software and the kind of networking and, frankly, distributed data storage types of systems that would make building a application distributed system, so microservices type architecture, that would make building something like that fairly straightforward. So you would see these kinds of systems in large companies. Like I worked for Goldman Sachs, and we definitely had service-oriented architectures all over that company, but they also had their own data centers, right? They had a lot of hardware. They had 10,000 developers. So there was a lot of independent software being written. But at a smaller company, even with hundreds of developers, you may not have done that because the accessibility and the speed in which you could spin up a new server was not quite there before the cloud release all of a sudden made that much easier.
Mm-hmm. So I totally agree with that, but let me just play devil's advocate for a second here. Let's say that I claim that the problem with that is that it's become too easy to build those things, and people build those things without knowing what they're getting themselves into. And all those problems that they have, because they now have a really strongly distributed system, are problems that they wouldn't have if they just stuck to their boring old database architecture. Maybe we should all stop pretending we're Google and just build simple stuff like we did it 15 years ago. Do you think it's well, I do not actually, I have to say that for my own reputation. I do not actually believe that, but let's just say that's a very valid argument. What would you say to that?
So I am actually more sympathetic than you might expect to that argument. Mm-hmm. Here is my personal take on all things is, don't buy complexity you don't need. And so I am a fan of, if your data will be reasonably usable in a relational database, you should probably, and you're doing transactions, you should probably use a relational database. Like if you really care about transactional, ACID, whatever, you don't want to lose data. Now, I realize that even the relational MySQLs and what have you of the world have failure conditions where they can do unexpected things, but they are so much rarer and so much more well understood by the operators out there in the world, and frankly by developers and other people, than the sort of MongoDB, Cassandra, yada yada world. That, I actually am very much like, we ran MySQL at Rent the Runway. We ran MySQL, as the transactional database because that was what was there when I joined, but it's a perfectly fine transactional database for what we were doing. Maybe we would have used Postgres if we were building it today. I certainly would not have used a, NoSQL or lighter weight distributed system to build that, because it's not worth reasoning about the edge cases when you're talking about something where you're taking money from people, where you're taking orders, where you want to make sure you're actually going to be able to fulfill those orders. So I am actually very sympathetic in being conservative where it matters. Now, I think the balance that you want to make with conservatism is the following. If it's truly faster for your developers to build things in a distributed system way, right? If it's truly faster for them to use certain types of systems for the type of data that they're working with, the type of volume that they're working with, the type of application that they're building, then they should probably use a distributed system, even if it has edge cases that they haven't fully considered. Because I actually think that the biggest cost to your business is developer time. Developer time is such a huge, huge, huge expense. And I think it goes both ways. I think sometimes we overbuild. We build too complex systems because we want to keep developers entertained. That's not a great reason to build a distributed system, is like cool points or, developer entertainment. But if you're building a system that you genuinely believe will help your development team be more productive, scale better, be able to get more business features out there, and you have an outage that makes you realize like, oh crap, the way we've been writing this data into this table is not good and we need to fix that. I think if you take a step back and you sort of quantify the potential for danger there, it's probably less than people think. You have outages of all sorts all the time when you're actually running a business, right? You have outages related to Hurricane Sandy flooding, flooding half of New York and cutting off your access to certain servers, right? You have outages because somebody at one of those big companies like Amazon screws up their distributed system and you didn't really know you were relying on that, right? You have outages because hackers attack you. You have outages because somebody fat fingers something. You're going to have failure and outages. You are not going to be able to think through every single possible edge case. And if you are deeply uncomfortable working in a world where you can have failure, then certainly I would say startup land is probably not for you. You may want to, look, there are places where this stuff is really like you don't have outages, right? You're building flight control software, maybe. You're building software to land a person on Mars, right? You're building certain kinds of financial system software. But for most people working in small to mid-sized companies, you are always going to be balancing the cost of building something and the cost of maintaining it over time and the risk of failure. That is just the balance that you do all the time. And so while I actually do think that, and I think you just need to make that conscious calculation as often as possible. So that includes being boring sometimes, and that includes taking something that may be a little bit flaky, but that's really easy and intuitive for your engineers to use and get started on and to run, like MongoDB, for example, right? MongoDB is incredibly easy for people to get started on and for people to use. And I think that's actually a brilliant aspect of that software, is that they realized that the startup cost for so many of the distributed storage systems at the time was really high. Actually, I'm not even sure that they built it that way because they were trying to compete with other people. That was just that for them, they felt like this was one of the usability element of the distributed system was a more important problem to tackle first than the correctness. And you may say that that's horrible and they're horrible people and how dare they tricked the industry. And I'm not going to argue either way on that. But I will say that I think that's an interesting choice that they have made. And that, people adopted it not just because they were idiots, but people adopted it because it was easy for their teams to use it and to get going with it, and they got value out of it. And so, you're making that trade-off on both to go conservative and both to go, sort of experimental. And as long as you're constantly thinking about where am I willing to take risks and where is it better for me to say, let's just favor developer productivity and do this, an easy way, or let's favor future scaling of developer productivity and put a little elbow grease into it now that will pay off when we have 50 developers or 500 developers, right? So, these things are really hard. I think these things are really hard, but I think that's the kind of trade-offs that you should be thinking about.
So it seems a lot of the things that you mentioned are related to areas where there is not that much complexity because the system is essentially stateless. You mentioned the web servers just scaling horizontally, and there was the implicit assumption, I guess, that these were stateless things. How do things change if we're talking about the stateful part, if we make that distributed? Yeah,
so I think state is where everything gets complicated, certainly. And I think when it comes to state, you want to be thoughtful about the level of consistency that you need for various parts of your data and understand really where are you comfortable having inconsistent state and where do you absolutely sort of need that consistency. So here's a great example from my past job, right? So I said, we relied on MySQL to be the transactional part of our data. So, and that meant that if you were placing an order, if you were making a reservation, that would go to MySQL. And we did that because I really wanted that stuff. I didn't want to lose that state, right? I wanted that state to be kept in a place that was, very, very core to the business. I mean, look, if the MySQL database went down, the business would not be able to function, right? There are core parts of every business, and So you're going to have some kind of system probably that's storing some of the data of the core parts of your business where if it goes away for whatever reason, it fails, the whole business or a large parts of the business are not going to be able to work, right? So when you're building a distributed system and you're dealing with parts that you really care about consistent state, you definitely get a lot of complexity there. In fact, so I'm a fan of use a relational database if you can for that part of your state, because those systems, again, as I said, tend to be more well understood. Now, you may still have to do things like shard it widely, which makes an incredibly operationally complex system. And there are many distributed systems aspects there, right? Where all of a sudden you're writing data to different places if you want to try to rebalance that data because one shard is getting full. How do you think about managing that rebalancing without taking your whole system down? Again, right, balancing that scaling versus failure tolerance that we talked about earlier. So you are definitely, I think one of the important things to think about as you're building out a distributed system is where do you care about coherence, consistent state? You don't lose data, you don't lose writes, you don't have people seeing different state at different, looking at the database at the same time and seeing different state. You want to be able to lock pieces of data so that multiple people can't update them at once, right? Things like that. You're going to have state, on the other hand, that's I think of it as cache state, right? My personal feeling is, if it's okay if people see slightly stale data, it's okay for it to be in a cache, right? And you want to think very carefully about where is it okay for people to see slightly stale data? Where is it okay for you to lose data because you can easily reconstruct that data, right? And those kinds of pieces of data you can serve them out of systems like, frankly, MongoDB, Redis, right? You can use systems like that. So for example, at Rent the Runway, we actually used MongoDB. We used it for both data that was more document-like that made sense. So our product data, right? We have lots of products. You've got to update them. They have lots of metadata around them. That was all stored in Mongo. That was stored in Mongo because, the process of creating that product, if we lost a piece, if we lost a detail, we could easily reconstruct it. It wasn't that big a deal if it was slightly incoherent or inconsistent for a little while, or if it was slightly, if you read something and then you read it again and you got a different version of it because it had been updated, but whatever, it just wasn't that big a deal. We were caching it in a whole bunch of other places anyway. So there was just not as much, it's not like you're placing an order, or if you hit place order and you place 4 orders, or you don't place an order at all, but you still think you did, that's a really terrible customer experience. So understanding where you can get away with thinking less about consistency, but where certain kinds of scaling might make your life easier, right? So again, caching, I think, is one of these layers where even if you were building, as you said, the parallel web server, the horizontally scaled web server, and okay, maybe doesn't have a lot of the challenges of a distributed system, you probably had memcache in there, right? And you probably thought about what you put in memcache, and you thought about, okay, what data matters if it changes, and I need to know that change immediately and evict it from the cache, and what data doesn't matter, right? What data can I put on a CDN? If I have a content delivery network, right? Again, if I'm serving websites, some of my data is going to be cached at the edge. So it's not even coming to my website, right? My images, things like that. Again, that's data where it's going to be stale. It might change and be stale for a little while. And that can be okay. So understanding, I do think that one of the major considerations as you find yourself building a distributed system, because you will, is actually an extension of the nuance of the things that you had to understand to even build kind of a working non-distributed system, which is what data has to be fresh, what data has to be locked, what data has to be, can only have a single writer and the readers must always see the updated versions of it, what data can be slightly stale, what data can be really stale and we don't care. What data if we lose a little bit of it, it's a bummer, but it's not like, like if I lose a little bit of the clickstream data on my website because I screw up, the analytics processing, that sucks. I've lost invaluable information, but I haven't lost any orders. I've just lost sort of metadata, right? So those I think those are some of the complexities that developers do need to understand. You need to have a basic understanding of when do you care about losing data and go from there. Because if you don't have that understanding of when do I care about losing data, then you cannot easily reason about a distributed system. If you say, well, I never want to lose data, that's not true. I don't actually believe that's true. I think most people, in fact, in most environments, they can say, okay, well, if I lost this click data, if I lost the fact that somebody faved this tweet, that's not good. I'm sure Twitter cares very much about, not losing that, but it's not like I lost somebody who gave me money placing an order. Right? We just have different thresholds of loss that we are willing to tolerate. And I think asking that question and then understanding the implications of if I use this type of system, where can I lose data? Right? Because that's the flip side of it, right? You will be able to lose data. Different types of systems will have different ways in which you can either lose or read stale data or, sort of see old results. And that's a big part of the balance that you're making as you build yourself into a distributed system.
A lot of the examples that you mentioned were or considered the actual application data, right? Like the order or maybe the product data. Another part of the data that a distributed system has to deal with is the actual configuration data and the information about the runtime setup of things. How do you deal with that? Yeah.
So that is definitely, I think, one of the places where you probably want it to be fairly consistent.
Oh, yeah.
In fact, I would say, so obviously I spend a lot of time talking about Apache Zookeeper because I'm one of the members of that project. And that was one of the original use cases for what I call consensus systems, which are systems like Zookeeper. Chubby is the system inside of Google that does this. That's built on Paxos. Systems that are built where every update goes through a consensus algorithm. So Paxos, again, is the classic one. ZAB, Zookeeper Atomic Broadcast, is the one inside of Zookeeper. There's also Raft, which is a new one that was developed, in the past few years. And there's a bunch of systems like etcd now relies on Raft. And all of these systems they have sort of, they do key value stores, but key value stores of not very much data. So the expectation is you're not storing a ton of data inside of these systems, but you're using them to make sure that if you write something and the system says, I got it, everybody who can access the system sees that update. And these are really useful especially for service orchestration type work, and large scale cluster management, understanding who is around and available and giving those people information. So distributed locking is another huge use case for these types of systems, right? If you need to elect a leader in your distributed system, which is going to be managing all the other processes of the distributed system in some way, right? You don't want to have a system that can give you two different leaders, right? If you have two leaders, bad things happen. So you use some kind of a consensus algorithm, and you may just use external consensus system like Zookeeper to store the results, to find the leader and store the results of who is the leader, so that you never have that situation where two people think they have what is essentially a distributed lock, right? Where you don't ever have that kind of situation. Similarly, you do want to have, the configuration of your global environment, understanding which servers are running and taking which data. That is generally a problem. Like, again, it depends on how stateless the servers might be, right? So there are systems out there that use like gossip protocols to identify servers that are running, which is slightly different than using like a consensus algorithm and having to actually sort of configure know where the cluster of Zookeepers is running, for example, or the cluster of etcd is running. Instead of doing that, you sort of use UDP and these gossip protocols to find other nodes on the network and get information through them. And so there are other ways to solve these problems. I'm honestly not nearly an expert in that. But I do think that when it comes to the operational complexity of running a distributed system, that's where people sometimes, I agree, actually they can get a little fast and loose with, well, I don't really care that much about, the accuracy of my distributed lock. I'm just going to use the database to write a distributed lock. And that's actually not a really awesome way to do distributed locking. Even though I think databases are great for transactional actions, that's a little bit different than what you need for distributed locking. And in particular, you probably don't want to have to poll a database to see if a lock state has changed. And these consensus systems all were built with the ability to notify you of state changes in the systems, which is really useful in cases where you want to immediately elect a new leader if one failed, so you don't have to do manual failover.
So would you say that every time you build a really distributed system, you should use one of those consensus-driven systems?
No. Well, first of all, if you're building a distributed database, you may very well just be needing to implement your own Paxos or your own, consensus state machine internally to do that kind of management, right? If you're trying to sell someone a product, you probably don't want to make them spin up a Zookeeper or an etcd or whatever, and then spin up your system, unless it's part of a larger ecosystem.
Right. Don't some of those tools do that anyway? I mean, some of the distributed systems,
so a lot of them actually...
Kafka, for example, rely on...
Totally, yeah. And I would say that they do because they were built within environments where there were already a lot of people using Zookeeper. So you can have a Zookeeper that supports a whole bunch of the sort of Hadoop family products, and a single Zookeeper can just be used to support that whole family of things because they're not writing that much data into them. And so, these systems being built in environments where they already had operators who knew how to operate Zookeeper, it was easier for them to build, assuming that there was a Zookeeper operational within the environment and not trying to build the state machine within them, rather than building the state machine within them. Because Kafka came out of LinkedIn. LinkedIn built it internally for their own usage. Now they're trying to spin it out into a real product that other people may buy and use. And so it will be interesting to see if they maintain the dependence on Zookeeper, if they decide to build some of that stuff internally. I don't know where they're going to go with that. But, again, for their audience, it may be reasonable to say, because so many people are using Zookeeper anyway, because many of them are already using Hadoop for things, they're using Spark or Storm or whatever. I'm never quite sure which products require Zookeeper and which don't these days. But, if they've already got it, that's not going to be the critical part of our roadmap to build it internally. That being said, if you look at Cassandra, if you look at React, you look at systems like that, which probably do have consensus protocols built internally, they're not relying on you having this centralized system, but they're still using consensus protocols and state machines in order to do that cluster management piece that they need to do and to do certain kinds of transactional operations that they want to provide. Now, you can run a distributed environment of microservices type things without having a lot of wholesale cluster orchestration if the pieces of your system are independent. So Rent the Runway, microservices or services, whatever the hell you want to call them. There were lots of services, right? We have lots of, servers running lots of services, but each service was developed to be deployable independent of the other services. So you don't need to do coordination there. Configuration was always deployed with the service. It wasn't dynamically changing. So we didn't really need it for that element. And we weren't quite at the scale where humans couldn't know, where humans couldn't sort of comprehend the scope of the entire system for pure operational perspectives. Meaning, like, if you have an operations person sort of saying, oh, we have a problem, it's in this server over here. Right? We weren't sort of adding new instances so quickly that we didn't even know where they were, and we didn't have IP addresses for them, and we had to like dynamically discover, oh yeah, I needed to auto scale out that service. So it got, automatically assigned to this server over there. We didn't have that level of dynamism. It was still a distributed system. It just didn't have the level of dynamism that required like a Zookeeper or other kind of service coordinator to really be managing it. And I actually think that's a good way to go. So we used load balancers to enable us to deploy with no downtime, right? You can use a load balancer to drain traffic off of nodes and update their software, and then put them back in the pool and drain the traffic off of the other ones, update their software, and put them back in the pool. That doesn't work if you break backward compatibility with your API endpoints. But breaking backward compatibility is such a major event, should be considered to be a major event in any architecture, that, I am very reluctant to build software that makes it easy to do something that I actually think should be a major event, because it's so easy for other things to break when you break backward compatibility, that it's just generally not a good practice for normal software development. So I don't think you have to have a consensus system if you have a distributed system of manageable scale where you don't have a lot of interdependence between the various services. You still have a distributed system, you still have multiple services, you still have some complexity, but you're not massively scaling. You're not trying to auto scale your cloud. You're not trying to just sort of throw a service wherever is available at the time and, assign it an IP and tell everybody, oh, hey, it's over here at this IP, right? You have a little bit more of a static environment that grows at human scale rather than at like machine dynamic scale.
That sounds like what a lot of the enterprise environments where people now start to adopt microservices look like, right? They will be much more static than a startup that might need to scale 100-fold in a week or so. So that predictability is much higher, and that seems much better suited to something slightly more static and slightly more reliable as a result of that.
Yeah, exactly.
Very good point. In the beginning, you mentioned that you have a history with Goldman Sachs as well as with Rent the Runway, and I believe I can't think of two companies that could be more different than these two. Can you talk a bit about the differences, both in software engineering and architecture, but maybe also in engineering-related organizational aspects that you experienced when you went from one to the other?
Yeah. So obviously, Goldman Sachs is a huge financial institution, and a lot of what I did working there was building big distributed systems. And so in many ways, actually, when I joined Goldman Sachs, I joined in 2005. And when I joined them, they operated very much against the business that you were supporting. So I worked in risk technology, and that technology team, which was about, the immediate team for the product that I worked on was about 60 to 80 people, let's say. And then the wider team was much larger than that. But we were very much dedicated to the risk management side of the firm-wide technology organization. And so we were actually, in many ways, able to act fairly independently. And that was somewhat startup-like. I mean, it was very enterprise in that, I had to dress up to go to work. Didn't have to wear a suit, but, and obviously we had all of this support around us. We didn't have to rack our own hardware exactly, although we did do what I would call much closer to DevOps than most people, I think, may have imagined, right? We certainly supported our own software in production and deployed it ourselves. We did not have an ops team that did all support and deployment. We did have, DBAs supporting the database, but we very much as developers of the software were also supporting it. And so I think there were actually a lot of things about those early experiences that were very similar to being in a startup, right? You're very close to the business. Your focus is building something that will be valuable for that business. You're not trying to, it wasn't moving that slowly. We had some freedom of choice about what kinds of software we use. Not perfect freedom, but we certainly, so it was not as different as working as a startup as you might expect. But it was, but then I worked in technology infrastructure, which was much more like big company, right? We were the big centralized infrastructure team for the entire company, which meant that, everybody wanted to have a say in what we worked on. And, our software could be used by lots and lots and lots and lots of teams. But on the flip side, we had much less freedom because we had to get so much political buy-in for everything we did. So that was actually what sort of drove me to leave a little bit, is I felt like in many ways, I loved the company. I had a very good experience. Goldman Sachs is not as evil as people might want to believe. Certainly not in the technology area. they're still engineers, So, and I got to work on some really large scale problems that were much, much, much larger scale than most people at startups will ever get to experience. And they had much harder requirements than most startups had to do. So I did have a lot higher threshold for, the risk management that I had to do. The last system that I built at Goldman Sachs was actually a global service discovery system. So I had to think about how to build this distributed system that would be available in Asia, in, the EU, in the Americas. And if part of it went down, I didn't want the whole system to go down, right? That would be very bad. It would be very bad if I built a system where, if for whatever reason, the Asia region was having technical problems and America couldn't get work done, that would be really, really, really bad. So you had to think much, much, really large scale. And, the amount of money that you were supporting and the amount of risk that you were taking on if you broke something was really high. Now, startup land had some similarities in that I think, the things that I learned at Goldman about really understanding and caring about the business that I was building and working fast, getting stuff done, shipping frequently, were things that I took to Rent the Runway. But I would say, the difference is, of course, that it's a startup. You have to do everything yourself. So, you really have much less support from those secret areas that you didn't even think about when you were working for a big company. We were running on cloud hardware, cloud networks, much less reliable than hardware, supported by dedicated teams inside of Goldman Sachs, where you really owned all the servers yourself. That wasn't a perfectly reliable world, but it was just more stable. It didn't change as much. And the cloud world, we had a lot more problems there. So learning about that kind of failure was really interesting. And then, of course, learning about just the stress and failure of growing a team and what kinds of things that, didn't work in enterprise that were really necessary in a startup. And it was some things that surprised me. I had actually never worked in an environment. Goldman Sachs did not necessarily have a lot of teams where every single piece of software required code review, which may seem surprising, but it was the case. It's not that we never did code review, and they may very well have that requirement now. But when I worked there, we did actually a lot of pairing. So we did a lot of pair programming and you wrote a lot of tests. So instead of relying heavily on code review, there was a lot more reliance on sort of the process around building software and validation. And so I was very reluctant to require code review at Rent the Runway. And my engineers at some point just kind of revolted. And they were like, the thing that's not working here is that we're not doing code reviews. And I was like, really? Okay, well, that's an easy one to fix. Now we have to do code reviews. And so, I think sometimes there's non-intuitive things that are actually harder and easier depending on the size of the company and the type of the company that people don't really expect.
Very interesting. Is this something you would take back from the lessons you learned in the startup world if you were to work for a big company again?
Oh, man. Yeah. I mean, I think what I would take back is, I think even at big companies, like Goldman was good, but only in places. People really get so far away from the business and the people that they're supporting that they lose their sense of what is important, what is valuable, what needs to happen. And you see that, frankly, people feel alienated at big companies because they don't understand why they're building what they're building. They don't understand who they're helping with the software that they're building. And it's very hard at a startup to get away from your customer. Frankly, I mean, at Rent the Runway, we actually let all the employees rent for free. The male employees would rent for their female friends or their girlfriends or their wives. And obviously the female employees, we would rent for ourselves. And so we all really got the experience of, being the customer, using the software as a customer would use it. We had a big warehouse where we did a lot of logistics, and we made everybody work a day in the warehouse. And the team that built the software for the warehouse went there very frequently and observed the processes and, actually did some of the work to understand the way the software they were building impacted that team. And I think, that is just such an important. Everybody pays a lot of lip service to this, I think, in startup land and in big company land, but it's easy to lose sight of how important it is that people be thinking about and reminded of why they're building what they're building, who they're helping, what matters to that person and what doesn't matter to that person.
Mm-hmm. Awesome. Camille, we're at the end of our time. Are there any last words you want to add? Some places you want to point people to? We'll have show notes, of course, but maybe one particular thing you want to add?
Yeah. Well, I mean, look, if you liked listening to me talk, I have many talks that I've given that are online that you can see. I suppose what I would point people to, just to take a step back from the general topic of distributed systems, I hope that what everyone took away from my conversation was, you are in a distributed world and you are going to need to think about that. I don't want to downplay that as a fact of life right now. But that doesn't mean you have to tackle every single problem. That doesn't mean that you have to expect that every system is going to be, perfectly reliable. And if it's not, if Kyle does a Jepsen test on it and reveals a weakness, that therefore that system is garbage and you shouldn't use it. We make a lot of trade-offs as engineers. We always have. Now we just make them at larger scale, and sometimes those trade-offs cause us sleepless nights and a lot of challenges, but you are always going to be making trade-offs no matter what you do. So try not to tackle every problem, tackle the problems that you really need to solve, and kind of work on developing a sense of where value lies in your business, where value lies in your software and your infrastructure, where it's reasonable to take risks and where it's not reasonable to take risks. And just developing those instincts, I think, will make the process of living in a distributed world, building distributed systems much, much easier.
Awesome. Camille, thank you so much for being with Software Engineering Radio, and to listeners, thank you for listening.
Thank you.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE Radio, or search for the Software Engineering Radio Group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.